Good afternoon, and welcome to my thesis defense. My name is Sam Hinks. I'm a PhD student at Tufts University. I've done this work for 6.5 years together with my advisor, Rob Jacob, and before that, for a few years with Leanne Hirschfield, who was Rob Jacob's former PhD student. I have recorded this video for those of you who are unable to attend the live dissertation at Tufts on April 30, 2019. And in this presentation, I'm going to try to condense a project that I've worked on for 10 years into a 1-hour presentation. I will therefore avoid details and, to the extent that it is possible, distill ideas to their essence. If you're interested in learning more, there's a fat dissertation waiting for you at samhinks.com. I will use these 60 minutes to set the stage for a paradigm shift in how we build and evaluate brain-computer interfaces. I will refer to this new paradigm as the physical paradigm because it is driven by models of how the brain works at all levels of analysis, beginning with the physical. This new physical paradigm enables what I refer to as a bidirectional brain-computer interface. A bidirectional brain-computer interface is a read-write brain-computer interface. It's a system that measures brain activity and uses this measurement to determine how to adjust output channels to the brain in order to bring it to more desirable states. So it establishes a bidirectional feedback loop between the brain and the computer. With a real-time physical description of the current state of the brain, the bidirectional BCI can use machine learning to optimize inputs to the brain that coerce a particular state. This is a very dangerous technology, and it is not clear to me that its net impact on humanity would be positive. This technology needs scientific supervision. And I should say that much of the thinking for this dissertation came in my years as a technological zealot. But today I'm quite worried about the impact of consumer technology on overall human well-being. To other listeners who are fed up with technology, I hope that the contents of my dissertation can be interpreted as a set of metaphors that help them take control of their own minds as human bidirectional brain-computer interfaces who can optimize the quality of mental states for themselves and other people. With that caveat aside, I will return to the technological image. There are two questions that need to be solved in order to build a bidirectional BCI. The first question, what I call the neurical question, asks, how do you construct an algorithm that measures brain activity on the basis of physiological measurements? The second question, what I call the stimulation question, asks, how do you adjust stimulation to the brain in order to induce desirable states? The first part of this presentation and chapter 1 in the dissertation will describe the approach used in the agnostic paradigm and show some functioning implementations of brain-computer interfaces. The second part, chapter 2, will expose 5 problems with the agnostic paradigm, focusing on the problem of entropy. And as we shall see, the problem entropy poses to machine learning algorithms is also the key to a solution in an algorithm that does not depend on machine learning. Chapter 3 will establish a neuroscientific framework for the physical paradigm, giving a principled way to begin to understand the meaning of neurological signals in terms of anticorrelated networks. Chapter 4 will give a new algorithm, what I call a physical neuracle, for classifying brain activity on the basis of anticorrelated networks. Chapter 5 will give a software program called Neuracle for building agnostic and physical neuracles. Its interface gives other researchers the opportunity to improve upon the specifications for a physical neuracle given in Chapter 4 and evaluate it on their own brains. Chapters 1 through 5 are primarily concerned with the neuracle question posed in the previous slide. How do you build an algorithm that classifies brain activity? Chapters 6 and 7 tackle the stimulation question. How do you adjust outputs to the brain to coerce optimal states? Chapter 6 investigates the degree to which electricity can be used to change brain states. Chapter 7 investigates the degree to which spatial information in music can be used to change mental states. So this research began in the field of human-computer interaction, where perhaps it still remains. I hope it still remains. It began with a simple question. How do you expand the bandwidth of communication between the human and the computer? In ordinary human-computer interaction, the user is limited to direct input devices, such as the mouse and keyboard, to communicate intention to the computer. The computer has no idea about its user's underlying mental state. But aspects of interaction could be shaped differently given the user state. For example, a task could be simplified if the user was cognitively overworked. An implicit interface improves aspects of interaction by knowing additional information about the user, which it detects through channels of input the user gives off non-intentionally. The computer knows something extra about the user's current mental state and cognitive capacity, and it adjusts internal parameters to serve the user. The first project I became involved in here at Tufts was an effort led by Dan African to build a dynamic difficulty adjustment engine by detecting the level of cognitive workload using FNIRS, or functional near-infrared spectroscopy. In this experiment, the user set the flight paths of UAVs in an air traffic control simulation. So the user is sitting by the computer wearing FNIRS, trying to make these simulated UAVs, between 3 and 7 of them, reach their destination without crashing into obstacles. When the engine detected that the user was in a low cognitive workload state, it added UAVs to the simulation. And when the user was in a high cognitive workload state, it removed UAVs. Compared to the control condition, there were significantly fewer failures in the adaptive condition, meaning users could guide the UAV to its destination with greater accuracy without crashing into those blue obstacles you see on the screen. So how do you build this implicit brain-computer interface? How do you power a dynamic difficulty adjustment engine in the agnostic paradigm? I have used the word neuracle a few times without properly defining it. A neuracle is an algorithm which summarizes the state of an information processing system, such as the brain, along a set of dimensions. I like the word neuracle because it reminds me of the ancient Greek oracle who predicted human fate. A neuracle may also be able to predict human fate by extrapolating rhythmic oscillations in brain activity. The word also reminds me of an octopus and its tentacles, which is a key metaphor for improving mental states for reasons I can tell you in person. So, an agnostic neuracle uses machine learning instead of neuroscientific models in order to classify brain activity. So, how do you build an agnostic neuracle? The approach we use in this lab begins with a brain sensor called functional near-infrared spectroscopy. This technology shines near-infrared light through the skin and bone covering the brain. The skin and bone is mostly transparent to the chosen near-infrared wavelengths. And so the amount of light returning to the detector, placed about 3 centimeters away, depends on the relative concentration of oxygenated and deoxygenated hemoglobin in the blood supplying energy to the brain. fNIRS therefore gives a similar approximation to the more widely used fMRI by the principle of neurovascular coupling, or blood oxygen level dependent. But fNIRS has the advantage of being relatively cheap to manufacture, lightweight and portable, so it's perfect for usage in human-computer interaction. And you can imagine the technology integrated in a hat or a wearable computer. In fact, a few years ago, we had a project funded by Google Glass's Academic Explorer program because there was the possibility to integrate fNIRS with Google Glass. So once you have the measurements coming from fNIRS, the agnostic paradigm for building a brain-computer interface can be partitioned into 5 steps. First, you calibrate the algorithm by manipulating the brain through a task. Then you process the raw signal. Then you extract features from the data. Then you build a machine learning algorithm on those task-feature pairings. And finally, you let the algorithm run in real time and power your adaptation in the implicit brain-computer interface. The calibration task typically used in implicit BCIs is the n-back task. In a visual one-back, you see a grid, and you must indicate whether the item witnessed at one iteration matches the one seen previously. The one-back is very easy and does not belabor a person's short-term working memory. The harder version is the 3-back. To solve a 3-back, the user must indicate whether the box matches the location 3 iterations ago. During the calibration period in a typical experiment of the agnostic paradigm, the user typically alternates between 30 seconds of the 1-back and 30 seconds of the 3-back. The raw signal is then filtered using a bandpass filter, preserving frequencies between 0.1 and 0.01 hertz, the stuff that fluctuates between every 10 and 100 seconds. Next, given the 3-dimensional data set, the next step in the agnostic neuracle is to extract features from the window of data. And I did an analysis of all possible features that I could think of, and I found the slope to be the most independently informative feature if you judge it by the accuracy of a machine learning algorithm who only gets to use one feature at a time. But you can throw any number of features into the machine learning, and it typically boosts accuracy, since the machine learning algorithm is designed to figure out how informative a given feature is. So other features that you typically extract from this window of data are the standard deviation, the minimum value, the time to peak, max, mean, slope, and second derivative of the signal. When you have your class feature pairings, the next step is just to feed it into a supervised machine learning algorithm. We found the most effective algorithm to be the support vector machine. The essence of this algorithm is to discover a hyperplane through a multidimensional feature space that maximizes the distance to different classes on either side of that line. And once you have this line, classification occurs simply by seeing where the weighted features fall relative to this hyperdimensional line. With a trained support vector machine, you can begin the main phase of the experiment. In the UAV experiment I just described, this is when the user begins to pilot the UAVs and direct them on the screen. And you can use the brain classification technique to establish an adaptive condition. So in this case, this is when the number of planes under user jurisdiction depends on whether the current brain profile looks more like them doing a 1-back or a 3-back. We've run a number of experiments in the agnostic paradigm, and some work and some do not work. I haven't had much success with this method, and so that's part of the reason why I spent a lot of trying to develop an alternative method, what I call the physical paradigm. There are 5 problems I can think of with the agnostic paradigm. These are inherent difficulties with the method for building agnostic neurals that must be solved, at least for these bidirectional brain-computer interfaces, which we'll get to. But I think it's necessary to power implicit BCIs that generalize beyond the laboratory context as well. And there are 3 problems in particular I would like to emphasize. The disengagement problem questions the ability to induce a state in the user. One person's 3-back is another person's 4-back. But the problem, I think, isn't really about intelligence. It's really more about attention. We cannot guarantee that the user is granting the full province of their attention to the task when they come in. A person could come into the experiment and they could just be thinking of something completely different while trying to solve the task. Another problem is the synchronization problem. Notice that when we calibrated the algorithm using an agnostic neural, we created these neat little trials with clear start and end points. But the information of the signal, the slope, is how it changes over time. And we need the algorithm to work in this live context where there aren't these neat trials. It's just a live feed of data and no clear delineation between the start of a task and then the end of the class. So actually the way that we have designed these agnostic neurals in these previous experiments, you'd really only expect them to work exactly once in the experiment, which is exactly 30 seconds after the experiment began, which has the same structure of sequences of mental states from a rest period to a point where you're 30 seconds after the start and can look back at these features that you've constructed over these 30-second time segments. Then there's a 5th problem, which I call the entropy problem. And it is both a problem and an opportunity. It states that each instance you give the machine learning algorithm for training should look slightly different because the brain has adapted itself, learning the particularities of each trial. Chapter 2 shows empirically how this is the case. looks at a study that evaluates the performance of machine learning algorithms or agnostic neurals in 2 sessions, one on one day and one on another day. Entropy is a term with overlapping definitions in physics, information theory, and neuroscience, where it's sort of a mixture of those two definitions. In physics, entropy is understood in reference to a microscopic state space producing a macroscopic phenomenon. Imagine a glass of water moments before you place a soluble vitamin C tablet on top. When the tablet is floating on the surface, that glass of water has low entropy. As it dissolves and the vitamins bind with the H2O compounds chaotically, the system exhibits greater entropy. In information theory, entropy is understood in reference to a system where there's a source generating data and some receiver interpreting that data. Some symbols the receiver gets are highly predictable, and others less so. You can quantify this with Shannon's formula for entropy as the average number of yes or no questions needed to ascertain the value of some variable coming from the source. For example, a coin has 1 bit of information. My favorite thing to do as an academic is to give people entropy by philosophizing about the relationship between entropy and consciousness. And I'm guessing there's a lot of uncertainty among listeners about the question about what consciousness is. Daniel Dennett claims it's an illusion, but I think it's the one thing that's real as a matter of our own perspective, which is all we have. In any case, there are a lot of curious and unresolved networks in the world, ready to latch onto and process new information related to this question. What you can say is that there are high and low conscious states, and it seems to be the case that consciousness is high when entropy in the brain is high. You can therefore increase the level of consciousness by giving new information about what consciousness is, assuming the receivers are tuned into the vocabulary that you're using and regard what you are saying as new information about consciousness. And what exactly it means for the brain to have high entropy is slightly different depending on whether you look at it, at consciousness from the inside out or from the outside in. And this distinction is similar to the distinction between entropy in physics and in information theory. Modern cognitive science conceives of the brain as a prediction and error correction engine. Imagine the brain as a hierarchical system that begins with the senses, eyes and ears, which transduce the field of changing energy in the external world. And the first responsibility of the brain is to arrive at a stable equilibrium with changes in the outside world. Like any other salient object that survives in the universe, it finds a stable equilibrium with this field of energy. And to do this, it builds these neural networks that in effect predict the causes of sensation, generating a sensorium that intelligently simplifies the complex world outside into a set of objects in 5 senses that afford action. when we're young, there's still a lot of learning happening in these hierarchically primitive structures that are immediately tethered to the outside world via sensation. And so consciousness, when we're young, fixates in the sensorium. But as we age, we learn efficient representations for explaining the inputs to our brain. And, and consciousness, therefore, becomes perhaps a little more stale, uh, or it's at the very least, it regresses into very hierarchically advanced endogenous structures. Still, we alternate between high and low entropy states, depending on our capacity to stabilize the reality that's in front of us and the amount of new information we receive. So we always risk going both into the low entropy depressive states and high entropy energized states. And one of the main points of my dissertation, perhaps the main point of this dissertation, is that if we get a good measure of entropy in the brain, we can build a bidirectional brain-computer interface that controls its user's level of consciousness, what I've called in another paper as an entropic brain-computer interface. So, to evaluate the degree to which the problem of entropy affects agnostic neuricles, we ran an experiment with 3 conditions using both FNIRS and EEG over 2 sessions. The 23 participants of the experiment were performing a low cognitive workload matching task for 35 seconds, then resting for 15 seconds, and then performing a more high cognitive workload addition task. And we therefore evaluated 2 agnostic neuricles on the experimental data. The first test compared how the classification separating the two tasks would change over 2 sessions. So the agnostic neuricle is attempting to distinguish between the user states when they are performing the matching task or the addition task. And in this test, there were no significant changes to the classifier performance from the first to second session. Then we trained a classifier to distinguish between the 2 task states, either the matching task or the addition task, versus the rest state. So those are 2 different labels for the data, either task or rest. This time, the agnostic neuricle decayed significantly in the second session for both EEG and FNIRS. And I believe the explanation for this is that in the second session of the experiment, the users had learned to perform the task, and therefore their task states looked more like resting states. In other words, it was the entropy inherent to the task that the classifier was noticing in the first session, and the task-induced entropy was lower in the second session, leading to worse agnostic neurical performance in that session. So instead of building agnostic neuricles, which suffer from the problem of entropy, you may be able to instead build physical neuricles that measure the brain's level of entropy directly from the signal. A physical neuricle is a program that classifies the state of the brain by a scientifically informed model of neural oscillations. In theory, a physical neuricle suffers none of the 5 problems of agnostic neuricles. Instead, the challenge is to link brain measurement to different states using scientific theory and math. The approach I am taking to build a physical neuricle proposes to think about the brain as 2 opposing factions engaged in a zero-sum war for oxygen. They alternate back and forth at timescales from, I don't know the bounds here, but perhaps a couple seconds to 100 seconds, or less and more. Uh, and consciousness fixates at one place at a time, or in the case of a default mode state, perhaps it's best characterized as a sort of blurring between exogenous and endogenous modes. One brain, what I call the exogenous brain, is tethered to the world via the senses. It adjusts internal representations so that it better predicts the causes of sensation, and it updates outputs like motor commands in order to create a sensorium with lower overall entropy, given the goals of a system to survive and replicate. The other brain, what I call the endogenous brain, is hierarchically separated from the world. It is perhaps best partitioned into two categories, one in which the directionality of the flow of data operates from the top down, and one in which there's less control as a matter of our agency, where the directionality flows from the bottom up, where internal models are penetrated by data. The endogenous bottom-up brain is also called the default mode network, which appears to be generating thoughts depending on where the human is in a hierarchy of needs. Activity in these two brains are anti-correlated with one another. When we are absorbed deeply in some task, we forfeit our internal monologue and lose our sense of self. When we are lost in our own mind wandering, we cannot effectively pay attention to the world. And there's an added complexity here, which I will mention only briefly in this presentation, but which is discussed more in the dissertation. Some expert listeners may be wondering what is the difference between the distinction between an exogenous versus endogenous brain and a task-positive versus resting state brain. As I see it, the task-positive brain can never be an endogenous bottom-up or default mode network brain, and the resting brain can never be a top-down brain. Task-positive versus resting is furthermore a distinction you can make externally about the user, and exogenous versus endogenous is this distinction you can really only make internally as the host of the system, the one who is generating or receiving or is equivalent to the conscious experience that is emerging. So in the upcoming experiment, I use the distinction of a task-positive and resting brain, but in the physical neurical I propose in the next chapter, I reason about the brain more as an exogenous versus endogenous system. Prior to my investigations with fNIRS, it was already widely known in fMRI literature that these two large-scale networks were anti-correlated with each other. So I set up an experiment that searched for anti-correlated networks in fNIRS data, trying to identify probe locations for an fNIRS-based physical neurical. And this was an experiment we did at Hamilton with Stewart and Leanne Hirschfield, among others. We measured brain activity at 52 probes, doing a near full head brain scan using the Hitachi ET G4000, which is a $370,000 device, but which we can build more cheaply, especially once we identify regions which are most informative towards the dimensions we are interested in classifying. We recruited 50 subjects for the experiment, and we ran the experiment 4 times on 2 separate days. Participants alternated between 3 tasks. In the addition task, the user added numbers appearing on a series of slides. This was meant to elicit exogenous task-positive network activity. In the resting task, the user was instructed to do nothing, which was meant to elicit endogenous default mode network activity. And finally, in the phone number task, the user subvocally rehearsed their phone number, and this was meant to elicit endogenous task-positive network activity, the top-down state. So the first 2 sessions, there were 4 sessions on 2 different days. And so the first day was used to make a selection about the 2 groups of channels in the brain, overall users, the task-positive brain and the rest-positive brain. So I created 2 clusters of the data to bin the channels into task-positive and rest-positive groups given FNIRS. To meet the criteria for inclusion into the task-positive group, the average oxygenated value over the 50 subjects needed to increase during the addition task. To meet inclusion in the rest-positive group, that value needed to increase over the controlled rest periods. The rest-positive channels were all in the prefrontal cortex, and the task-positive channels were in the midbrain regions like the temporal lobe. We didn't measure brain structures like the occipital lobe in the back of the head, but perhaps those would be more correlated with the task-positive condition. Next, I plotted the 2 groups, the task-positive channel set and the rest-positive channel set side by side. And what you see is 2 very strongly anti-correlated networks. On the top, you see a somewhat biased effect, since that data is used to make the selection. But on the bottom, you see a perfectly statistically valid effect, since those channels were not, those sessions were not used to make the selection. So you see that in this averaged data, the temporal lobe will generally increase in oxygen during the addition task, coinciding with the prefrontal cortex probes, ventromedial and dorsolateral, decreasing in oxygen. And I want to note also that getting this very clean data depends on a specialized adaptive filter, which I describe in detail in the dissertation. The essence of this filter is to characterize the frequencies of a systemic response, which you remove from each channel to get a signal that exclusively describes the brain. And I have since tested this on myself by shaving my head and using our lab's probes. And there is indeed a strong anticorrelation between a probe on the forehead and one by the ear, and it oscillates depending on the external information load that's coming from the environment. The easiest way to get a switch of which one is increasing and decreasing is simply by turning on and off the visual sensorium or closing and opening your eyes. So, in order to create a physical neuracle from anti-correlated networks, you need to create a direct mathematical mapping between fluctuations in these signal pairings and fundamental dimensions of consciousness, which you can describe from the outside in and from the inside out, which is key here, I believe, given the methodology that I'll propose in the next chapter. And in the dissertation, I propose that there are 3 basic dimensions that can be known at any given moment simply by introspecting one's own mental state. Of course, when you're in an act of introspection, that is itself its own state. Perhaps that's a top-down endogenous state. But one can look back at the mental states that just unfolded and characterize them in terms of these 3 dimensions. So all dimensions assume that any processing in the brain can be thought of as hierarchical prediction and error correction. When directionality is top-down, then the system is dominated by a deliberate control over the objects that emerge in consciousness. When directionality is bottom up, then the system is penetrated by new data and corrects itself for that new data. Power is a top-down state, and new love is a bottom-up state. When origin is endogenous, then the data being predicted and corrected for comes from within the system itself, from its repository of memories or from other internal signals such as the gut. When origin is exogenous, then the data originates from the external environment, and consciousness will fixate in the sensorium, which is quite nice. It's what being a kid feels like. When entropy is random, then the brain cycles unpredictably between many networks. This is likely to happen during bottom-up states when new information dominates internal models. But perhaps one can enter high entropy top-down states too by deliberately and creatively jumping between thought and different modalities. High entropy can also occur for inexplicable reasons, such as in an epileptic attack. And these as I said earlier, these higher entropy, the more random states, they give that tingling glow, the quality of consciousness. It has a higher temperature, I think, when entropy is random. When entropy is rigid, then the brain enters its default mode network state, and it just cycles haphazardly, perhaps predictably, at a rhythmic oscillation between endogenous and exogenous modes, without spawning any new and interesting networks. So I argued that these anti-correlated networks create the right conditions for building a physical neuracle, and there are 5 arguments that I put forth in the dissertation. The key really is that you can start to reason about the signal. You have 2 points of truth telling one story about how information processing flows in the brain. You can think of one side of the network as the one that is being perturbed by system input, the temporal lobe probe, and another one functioning more as an integrator of inputs, the prefrontal cortex probe. Since the 2 probes are anti-correlated, you know the 2 regions are engaged in a form of dialogue, and it is the dialogue between the 2 channels which holds the information. So the physical neuracle I propose looks at statistical features from this pair of signals to extract dimensions about the user state. Chapter 4 gives my hypothesis for how to build a physical neuracle. I will not go into depth of how this algorithm works in the presentation, but I will give its essence. At the neuracle level, it's a 3-step algorithm, which requires 3 FNIRS probes, 2 endogenous probes on the forehead or the prefrontal cortex, and 1 exogenous probe placed on the temporal lobe. Then after those 3 steps, there are 2 additional steps describing how to map these dimensions onto changes in any brain-computer interface, implicit or bidirectional. So the calibration period for the physical neuracle can be very short, unlike for the agnostic neuracle, which must witness the brain under different conditions. Here you apply a set of filters first to the raw data, including the crucial adaptive filter. And you're simply adjusting probes in the brain to find the highest possible anti-correlation between probes by the forehead and probes by the ear. it may make sense to give the users different tasks while you do this probe adjustment, but this remains untested. Next, the physical neuracle begins to segment the data into chunks over which it can extract features. Remember that in the agnostic neuracle, the segments, the length of the segments was static. So each trial had to be, some predetermined value, such as 20 seconds or 30 seconds, depending on how you design the calibration period. In the physical neuracle I propose, the length of a given segment is dynamic, so that sometimes a given unit could be 3 seconds, or at other times it could be 100 seconds. It creates a new segment every time the cycle between the endogenous and exogenous probe shifts. So in an anticorrelated network, only one of the two networks should have a positive slope. And every time this shifts, you create a new segment. It's also worth mentioning that in the dissertation, I speculate that the current length of a segment is itself a critical dimension of consciousness, describing how long you're lingering in a particular network. This may be the best approximation we have of the flow state with Fnir's data. So given these variable length segments, the next step of the algorithm is to extract dimensions whose meaning can be reasoned about directly if you understand this information processing vocabulary. Chapter 4 of the dissertation shows 13 dimensions, but there are 3 which I want to describe here, the 3 already mentioned. And I want to say also that these should be regarded as hypotheses, and I'm making positive assertions here, which others can falsify using the software I give in the next chapter. This is very hard to falsify science because it depends on introspection. So whether the user is in a top-down or bottom-up state is determined by which one of the 2 anticorrelated networks has a higher anticorrelation. So there are two basic networks which I found as in chapter 3. One between the lower forehead and ventral prefrontal cortex and the temporal lobe, and one between the upper forehead or dorsolateral prefrontal cortex and the temporal lobe. So if there's a stronger network being spawned between the dorsolateral prefrontal cortex and the temporal lobe, then perhaps the user is in more of a top-down state, and they're in more of a bottom-up state if there's more of a dialogue between the VM PFC and the temporal lobe. So whether the user is in more of an endogenous or an exogenous state, meaning the state is driven from internal inputs or from external inputs, is perhaps determined by where they are in the anticorrelated network cycle for either one of those 2 networks. When oxygen rises in the temporal lobe, then they are classified as being in an exogenous state. And when it goes up in the prefrontal cortex node, then they're in an endogenous state. Finally, the entropy dimension is a bit more complex and involves looking at historical data as well as new data and classifying how unpredictable the current dimensions are given the historical dimensions. So that ends the neurical part of the physical paradigm. The next step in brain-computer interface is to map these dimensions onto actions you can take within the user interface, what I call creating imperative objects. And I propose that there are three basic imperatives which encapsulate most changes you would want to make in both implicit and bidirectional brain-computer interfaces. Continue is positive when the brain is in a good state. Simplify is positive when the brain's cognitive capacities are overworked. And interrupt is positive when it's a good idea to give the user more information. And again, I have hypotheses for how these 13 dimensions can be mapped onto continue, simplify, and interrupt. But again, they are just hypotheses, and you can read more about them in the dissertation. So you should think of these imperative objects as these variables that change based on brain activity, which a programmer can reason about without knowing anything about how the brain works. Just like programs trigger changes to internal elements based on functions who listen to mouse and keyboard input, a brain adaptive program can change elements depending on how the values in the imperative objects continue, simplify, and interrupt change. So the dynamic difficulty engine and bubble cursor experiments described in chapter 1 would have both made use of the simplify object. And another Google Glass experiment we did, which put additional information in Google Glass at times when the user could process additional information in this peripheral screen, would have made use of the interrupt object. And the bidirectional brain-computer interfaces that I described in chapters 6 and 7 would use the continue object to discover how to adjust inputs to the brain so that continue is always positive, meaning the brain is in a good attentional state. To recap what we have done so far, in chapter 1, I introduced the current state of research in F-near-space brain-computer interfaces, referring to the methodology as the agnostic paradigm for BCI. In chapter 2, I exposed 5 problems with the agnostic paradigm, focusing on the problem of entropy, which creates a bridge to a new physical paradigm, where the brain is understood as a system poised between order and disorder depending on its degree of surprise with system inputs. In chapter 3, I propose that building a physical neuracle that understands the meaning of neural oscillations depends on decoding anticorrelated networks in the brain, and the strongest anticorrelated network in F-NIRS data can be found with one probe on the forehead and one by the ear. In chapter 4, I gave a hypothesis for what changes in the signal meant. This chapter was somewhat speculative and based on my history of analyzing F-NIRS signals on others' brains and also on my own. So in chapter 5, I give the software that is necessary for others to verify, falsify, and improve upon these hypotheses. The software is called Neuracle and is available open source. From the user's point of view, Neuracle has 3 primary components. The data view is where any data object, saved or real-time, appears. Neuracle is designed to keep track of the relationship between data objects as they are manipulated and transformed. This enables the user to explore different filters and pre-processing steps and also to undo their choices by going back to the previous object. In the image, the data has been transformed from a 2-dimensional organization into a 3-dimensional organization of different instances with a common class. The visualization component, up here to the right, displays data. There are different visualizations depending on the type of object being clicked. The visualization here shows a 3D data set so that instances with the same color belong to the same class. Other types of visualizations, so the whole data set organized in only 2 dimensions, and also real-time streams of the data so you can witness changes in brain activity as it happens. The console view is where the user enters commands and creates new experiments and manipulates the data. There are tons of commands implemented in Neuracle that are useful for rapidly testing and evaluating hypotheses regarding physical as well as agnostic neuracles, as well as connecting these classifications to external applications through ports. For example, Neuracle can initiate protocols for labeling data using the stream label command. Neuracle can initiate cognitive workload induction tasks using the nback command. Neuracle can be used to build adaptive filters for physical neuracles, and one can train many different machine learning algorithms for agnostic neuracles. All these commands, along with documentation and parameters, are available by entering tab into the console. So the key affordance of Neuracle is that it enables users to rapidly test and iterate upon hypotheses for how to build these neuracles. The idea is to let the one who is adjusting parameters of the Neuracle be the one whose brain is being examined, so that they can introspect their mental states and assign better labels to data and adjust them in response to real-time changes as a sort of neurofeedback mechanism. Here are some commands you may use in Neuracle. In the first image, you see raw data before any processing is applied. In the next screen up here to the right, you see a new data set that is the descendant of the first one. Here the user has applied the adaptive filter command to the data. Next, here in the bottom left, the user has applied the split command. This transforms the data from its 2-dimensional representation into the 3-dimensional representation into instances. And finally, here in the bottom right corner, the user has applied the keep command to hold on to only instances of the conditions under analysis. The dissertation contains a brief introduction to the source code, which is made available at GitHub. Neuracle is implemented in the model view controller paradigm. The user interacts with a front end that is implemented in JavaScript, CSS, and HTML. The models of the data and the processing commands are all implemented in the back end using Java. And I use the Stripes framework and Ajax in order to establish a communication between front end and back end. The code is reasonably documented, and I hope others will make use of it and extend it. So there are 2 questions for how to build a bidirectional BCI. The first question, what we have been exploring, is how you build an algorithm that measures the user's mental state. By Chapter 5, I end my exploration of this question by releasing software that enables others to evaluate and refine the hypotheses that I've given in the previous chapters. The remaining 2 chapters are dedicated to the other side, which is how to adjust inputs to the brain in order to coerce desirable states. Chapter 6 explores the possibility to manipulate the state of the brain using electricity with a technology called transcranial direct current stimulation, or TDCS. So we conducted 2 experiments evaluating temporal properties of TDCS. You need there to be an immediate effect of stimulation in order for it to work in a bidirectional BCI. So if you're making, the idea is to tie this all together in a real-time loop, and you need for the effect associated with the stimulation to register immediately if you're going to have a feedback loop. between measurement and stimulation. So we conducted these two experiments evaluating temporal properties of TDCS. In both the experiments, the user alternated between different difficulty levels of the NBAC for 15 minutes. At the end of each NBAC, which lasted 40 seconds, we collected the accuracy at the NBAC trial. And so ideally, after just 1 minute, there would be a boost in cognitive performance by TDCS. Half of participants received placebo stimulation, which made them believe that their brain was being stimulated by TDCS, and half of participants received real stimulation. In the first experiment, stimulation lasted 5 minutes, and in the second experiment, it lasted 10 minutes. And we evaluated both reaction time and accuracy at the NBAC at the end of each minute. And there were no significant differences in experiment 1, where stimulation lasted 5 minutes, and in experiment 2, where stimulation lasted for 10 minutes in the real group, and there were 14 participants. There were significant differences, but only in the 9th minute of stimulation. But this improvement came to both reaction time and accuracy, so it may have been a robust effect. But given that there's only one significant minute here, we don't necessarily know exactly what's going on here. But we can certainly conclude in either case that TDCS is not useful for a bidirectional BCI, because in the best case it takes 9 minutes to elicit a cognitive boost from TDCS. So we aborted this dream of making an FNIRS based decision maker for how to administer electricity to the brain to coerce cognitive improvements, and we tried an alternative method, what you may call a form of audio stimulation. So music is the most ancient way to hack the sensorium using entropic principles to alter the predictability of information to the brain. Music is a layered set of sound patterns at different time scales, whose information is processed by neural machinery that are incidentally connected to different emotional structures, depending on what primitive or learned associations are conjured by the sound. The question for a bidirectional BCI would be, what aspects of sound can be parameterized to control for the level of information of input to the brain? And Chapter 7 promotes one answer to this question as the amount of motion in the sound. Although it is beyond the scope of the current PhD to fully explore the cognitive science behind this question, but I believe the fundamental role of sound perception is to decode the changing position and orientation of objects in 3D space. The rules in music may therefore be a sort of reverse engineering of plausible movements of sound in 3D space and the associated acoustic vibrations entailed by these movements. But during ordinary playback of music, you hear sound in a two-dimensional space. You hear it just coming from two speakers or in headphones, for example. But to hear a song in its highest information version, the inherent motion sequences of the sound, which have been created by the musician, da-da-da-ding, da-ding, are actually rendered physically in a physical space. So da-da-da-ding, da-ding. You see this, you can almost imagine that this sound is moving up and down, moving towards you perhaps, or moving away from you. So when you hear this sound in 3 dimensions, there's more information in the underlying signal, and thus more neural networks must participate to decode this signal. Crucially, also, there's redundant information between the spatial predictors and the underlying music. So you spawn in the brain a large interconnected information where the sound decoders can contribute to decoding the signal. So you create this larger network that's active at once, which registers as a more rich exogenous state for conscious attention. And it is possible to simulate the sensation of moving music by closing your eyes and letting somebody slowly move speakers around your head at the pace of the music. And if the sound is right and mapped appropriately to a movement in 3D space, the associated experience is very rich and unusual, and it varies person to person. It's very interesting to see the unique experience a person has to it. We call this a music massage, and I've music massaged several hundreds of people, and the feedback is diverse, but nearly everyone reports this rich and unusual mental state. In one case study, my friend Mike Gabor and I went to an arts festival, and we had a little camp hidden in the woods called the Sensorium. We walked around the festival handing out riddles, which, if solved, disclosed our location. And attendees arrived, and the attendees who solved the riddle arrived, and we gave them a menu of pens from which they could select a mental state. So they could say, oh, I want a light blue state, which corresponds to sort of a relaxed, calm, and serene feeling. Or else they could pick from any one of these 10 colors. And this controlled the song that we selected. Then they lay down in a hammock, and we put on blindfolds, and we just moved speakers around their heads at the pace of the music. Afterwards, we gave them the colored pens and let them draw in our guest book, asking them to try to capture what they saw or felt. And some added messages to the notebook, like, I think this is the best thing I've ever drawn. People were really put in a good state at the Camp Sensorium here. And actually, by the fourth day of the experiment, when word of mouth had spread about this, demand outstripped supply for a music massage, and we actually were forced to give a music massage to about 20 people at once. And you learn a lot about the sensorium, because you really only seen your own sensorium, but you learn a lot about other people's sensorium when you create this atmosphere where people feel comfortable focusing on it and describing it afterwards. And so some people get a very tactile sensation from this. Others, it's a full, rich audio sensation. Others get many ideas. And some people actually see full visual scenes in color when they receive a massage. Surprisingly many people, actually. I conducted a more focused study on one such, what you might call a semi-synesthetic individual. So for this, I color-coded 83 songs that I had made for the music massage, and I music massaged 19 of these songs on this person. I wondered whether a song that I color-coded, for example, as orange, had a greater probability of inducing an orange-colored sensorium. So her eyes are closed, and while she is receiving this music massage, her brain is generating a scene fitting the music. And afterwards, I ask her what she saw, and she's remarkably good at remembering the scenes afterwards. The scenes are fascinating and inspire my choices of album art for the song when I release it. My favorite is for the song that is codenamed These Days. where she sees the face of an old man engraved on a tree. Uh, so I don't know exactly how to make a study out of this. It's just a case study here. But in all, I music massaged 19 songs, and 18 of them led to these scenes. So it really suggests the interesting possibilities for a bidirectional brain-computer interface that writes images in brains through sound, uh, and and that can be used for fun or insight or just a connection between uh, the person receiving the massage and the one giving the massage. Mhm. So, in conclusion, there are very many technical components of a bidirectional brain-computer interface, and I've partitioned my analysis into two questions, which is how you build this neuracle and how you adjust stimulation to the brain based on what this neuracle can measure. And the approach I've taken to build this neuracle has been to latch onto anti-correlated networks in the brain between one probe at the temporal lobe and one probe at somewhere on the prefrontal cortex. And I believe the anti-correlation between these two regions depends on the fact that the brain has two large-scale families of networks, one of which is connected to the world and varies depending on the information processing burden posed by the world. And it's anti-correlated to a more endogenous network which operates primarily on signals from the brain's repositories of memories. So this is sort of the brain's default mode networks, the running succession of thoughts that have nothing to do with what's in front of you. So with this theory for what the meaning of these anti-correlated networks in FNIR's data is, I've given a theory or an algorithm for extracting 13 dimensions of a user's cognitive state, and future research should verify these hypotheses. I've asserted that, most crucially, the given physical neuracle can measure whether a particular conscious state is more controlled from the top down than the bottom up, whether the data being acted on originated from within the system or from the outside, and the degree to which the particular mental state was normal or unusual. I further believe that it's really only possible to fully test this algorithm by introspection. So you cannot figure out from the outside what the mental state is, because you could be doing a task in the world, but conscious attention does not necessarily need to be fixating with the sensation of doing that task just because you're doing it, because it could have a very implicit mapping, and when there are implicit mappings solving a problem in the brain, then conscious attention can actually fixate in default mode networks instead. And so you need a system for being able to label the data by introspecting your own cognition. And for that reason, I built and distributed the neuracle software, which I hope others can use to develop upon these ideas and refine the hypothesis and algorithm. So at the stimulation level, future research should map out the space of safe forms of stimulation to the brain that satisfy the properties that would qualify them for bidirectional brain-computer interfaces, mainly the temporal component, which is what disqualified TDCS in our analyses. I have found the motion of music to be the most promising candidate, but unfortunately it's very challenging to do justice to a music massage in headphones. The sound actually needs to move in a 3D space. But with all components of the bidirectional BCI fully automated with the physical numerical algorithm working, and with some way to mimic the motion of sound using moving speakers. Uh, it's possible to, I believe, build a very powerful way to hack the brain, uh, by making so that parameters of the sound or whatever the form of stimulation is depends on the state of the brain. So, for example, when the brain enters its default mode network, meaning conscious attention no longer fixates with the contents of the sensorium, uh, the interface could ramp up the level of information in the signal that the brain must process, and bring attention back to the sensorium, and in effect abort processing in this default mode network, which may not be an as satisfying home for cognition, or certainly not a productive one if one is trying to solve a problem. So for example, the music could be in this low information mode where there's nothing unexpected happening, no movements, and then when the default mode network becomes active, it could start increasing the motion of the sound, and sort of slowly guide user attention back to the sensorium. But in either case, future research should monitor this technology with strict scientific supervision, especially given the cultural context of 2019, I believe. In some people's reckoning, the last thing humanity needs right now is more addictive technological superstimuli. In fact, my highest hope for this dissertation is not necessarily that the underlying technology is implemented. Instead, I hope the software and abstractions can be used in the service of facilitating meditation, human connection, and insight. And with that, I would like to thank you for listening and invite you to ask any questions you may have via email or however you can reach me. And have a great day.